Hi, this is Blake Smith from section MO4. This lab deals with Newton's second law, which states that based upon the initial velocity, mass, and net force, you can determine the object's final velocity. Newton's second law is derived from the momentum principle, which states that momentum is equal to mass times volume. If you take the derivative of that, you find that the change in momentum is equal to the mass times the change in velocity. However, because the change in momentum is equal to the net force times the change in time, you can combine the two equations to get the more practical equation: final velocity is equal to the initial velocity plus the net force divided by the mass times the change in time. In this lab, I use Newton's second law to predict the position of an object using the initial position and average velocity, assuming there was a zero net force associated with the movement of the object. You can assume there is a net zero force because there are not any other observable forces and the ball is moving with a constant velocity in a single direction. In my lab, the object was a soccer ball I rolled in a straight line. I took a video of that motion using my phone, and then I put that video into a program called Tracker. I tracked the motion of the ball every 0.33 seconds, and recorded the results in a chart, which could be used to graph a line. I took the data from my video so I can compare it later to the theoretical data that I found using Newton's second law. To find this theoretical data, I used the programming language Python to simulate Newton's second law using the equation v sub f is equal to v sub I plus f net divided by m times delta t. And the integral of that equation, the final position is equal to the initial position plus the average velocity times the change in time. To determine the ball's theoretical position based upon the initial position, mass, zero net force, and average velocity, I took the average velocity found by using the first and last position and times from the tracker data and used that in my program in Python. I then graphed the two sets of points on the same plot to see how close the theoretical data is to the observed data. Here's the graph that was made from the predicted values from Python and the observed data taken from Tracker. There is a slight discrepancy between the two sets of values, which can possibly be explained by either friction or human error while using Tracker. Other than that small discrepancy, the program of Newton's second law in Python was very accurate to the observed position of the ball. If I switched the direction I rolled the ball, I would have the exact same magnitude of the ball's velocity. It would just be in the other direction. In conclusion, I did an experiment based upon Newton's second law, and I found that the observed data was very close to theoretical data taken by using Newton's second law.